Hi, my name is Bryant and I'm a development engineer for Texas Multicore Technologies. This video is the last of a three-part tutorial series. In this video, I will be exploring some anecdotal evidence of the read and writability of SequenceL as well as the effects of autoparallelization. We will start with an anecdote of readability. In 2008, NASA was working on the PEG system for a space shuttle. This is a system that determines where a spacecraft will be in 2 seconds as part of the shuttle abort system. If there is a malfunction, depending on the severity of that malfunction, the spacecraft will either attempt to land at a runway or be forced to abort into the ocean. The C code that had implemented the system appeared to work, but it didn't seem to implement its specification, and the people who had worked on it had left. As a part of a NASA grant at Texas Tech University, the C code was ported to SequenceL. NASA personnel said that they could read the code immediately. Not only was it easier to read, but bugs were revealed in the C code during the port. For an example of readability and writability, we will look at matrix multiply. Matrix multiply is an operation that most people are familiar with, and which many have implemented themselves. This makes it a perfect candidate to explore reading and writing it in SequenceL. Here we have the mathematical definition of matrix multiply. The ijth element of the result is the dot product of the ith row of A and the jth column of B. If we were going to write this in a procedural language like Java, we would need something like 3 nested for loops. Also, the resulting code looks nothing like the definition. In fact, there's a small error in this Java code that you may not even have noticed. Here we see matrix multiply written in SequenceL. It's a 2D index function in which the ijth element is the dot product of the ith row of A and the jth column of B. If you'll recall the all keyword from the previous video, we can simplify this even further and write it on a single line. You'll notice this looks remarkably similar to the mathematical definition of matrix multiply. The parallel implementation of matrix multiply, written in C and MPI, is 130 lines of code with a few comments. An example of this can be found at this link. Parallel matrix multiply in SequenceL is the same line of code thanks to SequenceL's automatically parallelizing compiler. But how does SequenceL's parallel matrix multiply perform? We'll now take a look at the effects of SequenceL's automatic parallelization. Here I've plotted the speedup of the single-line SequenceL matrix multiply on various core counts, comparing it to the sequential C++ implementation. Since SequenceL is capable of changing the number of cores it runs on at runtime, the developer is easily able to produce similar performance comparisons. Here, we see as the number of cores is increased, the SequenceL code gains a nearly linear speedup. In fact, the SequenceL running on one core is faster than the sequential C++ code running on one core. Here, we see similar data from many other SequenceL programs written by both customers and TMT developers. You'll notice that most of the programs gain nearly linear speedup, with 2D FFT and Game of Life performing the best. In fact, even LU factorization, an inherently difficult to parallelize algorithm, benefits a great deal from automatic parallelization and is able to make use of many cores. To finish up, we'll look at an anecdote of SequenceL's performance as well as its ease of writing. Emerson Process Management recently developed a new wireless HART algorithm for large process control environments. The paper on this algorithm was presented to IEEE and won an award. Emerson asked us to implement the algorithm in SequenceL alongside the inventors implementing it in Java for a case study. We were given only the white paper and began working. The SequenceL code was finished in 3 weeks, including the time it took to become familiar with the algorithm. It took the inventors 3 months to finish it in Java, and it wasn't even correct. Once they finished, we compared the results of the code to find that they were different. It turned out that the Java code was incorrect, and the SequenceL code was then used to debug the Java. After a 4th month, the Java code was finally debugged, but it was still 10 times slower than the SequenceL code on just 2 cores. A 5th month was spent getting the Java code to perform 3 times slower than the SequenceL code. In fact, they were unable to get it to perform fast enough to meet specification. In the end, the SequenceL code was finished in 15% of the time, was correct out of the box, and outperformed the Java code by 1.5 to 3 times on a 2-core machine. Thank you for taking the time to watch this video. If you have any questions or comments, feel free to comment on this video or contact us via our website, which is linked to in the video description. If you're interested in learning more about SequenceL, be sure to subscribe to this channel.